In this video, I want to talk about a special case of permutations that we haven't talked about yet. So to segue into that, let's review with a type of permutations that we have done. Let's say that we want to start with the letters in the word wind and make a 4-letter password out of those letters. All right, so we know a couple ways to count how many passwords that would be. We could do fundamental counting principle. There would be, and then let's also specify two, maybe no repeats here. Okay, so if we wanted to, www would not be a valid password. That would, maybe be too easy. So maybe we want to make it a little bit harder. So if we use fundamental counting principle, we know that we're assigning, we have 4 different letters to choose. So we have 4 letters that could be the first letter. Okay, it could be any of those. And then as long as we know that there are no repeats, then we know that there are 3 letters that could be in the second spot in the password. And then we'd have 2 left to choose from for the third spot, and then finally we would be down to just 1 letter that's left that would have to go in that last spot. So by fundamental counting principle, we know we can find the total number of passwords by multiplying. So that would give us a total of 24 different passwords. We also now know that this is a permutation, so we're looking at arrangements or orders of these letters, and that's implied by the fact that it's a password. So in other words, we want to say that wind is a different password than if we wrote all those letters in reverse. So the order does make a difference, and it should be counted as 2 different passwords. So now that we know that, this is a permutation of 4 different things. Out of 4, it's all of them. So this could also be described by doing 4 factorial, or we could do 4p4. We're choosing 4 out of 4 things and putting them in a certain order. All right, so there's our 3 methods so far. We have fundamental counting principle, we have a factorial, since we're choosing all of the letters that were available as options, or we could use a permutations rule. So that's something we've talked about before. Now let's look at a problem that is similar but different in one key respect. Let's say now that we're trying to make 4-letter passwords using the letters in the word moon, and still no repeats allowed, how many different passwords could we make? So initially it almost looks like it would just be the same, right? We have a 4-letter word, M-O-O-N, and we're making a 4-letter password, so we have 4 options for the first letter, 3 for the second, 2 for the third, and 1 for the last. So it looks like there should be 24 different passwords. However, maybe you are noticing that there is something different about moon than wind, and if not, I think that would be clear if we list out what are all of these 24 different passwords. So let's make a list here, and this is a bit tedious, so we're not going to do this more than once here, and then there definitely is a shorter way. So let's list first. We've got all of the passwords that start with M. Okay, so we've got M-O-O-N, maybe it's M-O-N-O, or maybe N-O-O. And then what about all the passwords that start with N? So I would have M-O-O, or maybe it's O-M-O, or O-O-M. And then what about ones that start with O? It could be O-N-M, it could be O-M-N, it could be, the last 3 letters could be M-O-N, or they could be N-O-M, or maybe it's O-N-M-O, or O-M-N-O. So take a look at this list and see if you can find any that are missing, or if you feel like this is a complete list. All right, so this was the organization scheme, so I looked at ones that started with M, started with N, or started with O, and then just looked at rearrangements of the other 3 letters. Okay, so these are certainly all different, and we're looking for the number of different passwords. All right, so if you count these up, you'll notice that there are actually 12 passwords here and not actually 24 as we would have expected maybe with that permutations formula. So where are the other 12? That's the question. And you may be onto this by now and you can see why we're missing 12 of these things. The issue is that unlike the word wind, which had 4 different letters, we actually have 2 O's in the middle of moon that look the same when we're constructing these passwords. All right, so if you just do the permutations formula, it doesn't know that those O's don't look any different. So 24 would count ones that actually look the same, but would technically be a different arrangement. And I think we can make this clear if we call these O's like O1 and O2. Right, so if we were able to sort of distinguish between them, well then, looking at this password moon, right, I don't know if that's O1, O2, or O2, O1. And I don't care if I'm counting just the number of different passwords, so it doesn't really matter when you're listing those out. But for every single one of these 12 options that's listed, there's actually another one that we didn't list where the 2 O's are switched. Right, so like this very last one, this might be like O1 and then O2 at the end, and in that case I would not have listed O2, M, N, O1. Right, so switching the O's would give 12 more passwords. Alright, so if we looked at another word with maybe some repeat letters, like what about the word zoology? Alright, so now I have 3 repeat O's, and I have more letters. So if we do the permutations formula, this is 7 letters, and let's say I'm making a 7-letter password with no repeats. Alright, well then the number of passwords or the number of permutations, this is either 7 factorial, right, or you could think of this as 7p7. I'm arranging all 7 of those 7 letters. Okay. And that would give me 5,040 permutations of 7 different letters. Okay, now again, the issue is that that's counting all of the ones that would look similar, and in reality I only want to count the ones that are actually different. All right, so for example, if we even just look at zoology arranged, the letters arranged the way they are, okay, I've got some O's here that I don't actually know which one is which. Right? So if you think about the different options, all right, it could be that O1 is first, and then O2, and then O3. It could be O1, O3, O2, or it could be, you could have O2 first or O3 first. All right, so technically, in this count of 540 passwords, okay, all 6 of these options have been counted. And the same thing would be true even if we looked at a different arrangement of that. So like, let's say it was just written backwards. Let's see. Like that. Okay, then that would be counted as one of the 5,040 passwords. Okay, but there would actually be, this would be kind of written 6 different times to account for those O's being in 6 different arrangements. Alright, so the question now is how do I go from this 5,040 number, how do I find the number of permutations that actually look different from each other, the number of different passwords? Right, so in the moon problem, we had to cut down 24 passwords to just 12 different ones. And here I want to take 5,040 passwords and eliminate all of the repeats, the ones that would look exactly the same, but would technically be counted multiple times because of the O's. And I want to just count that like a single time. So like zoology backwards, I just want to count that once. Right? So the key is in recognizing how many different ways there are to arrange that letter that's repeating. So in the moon problem, if you have 2 O's, let me do a new page here. So if you have 2 O's, and you look at how many ways there are to arrange them, well, that's just 2 times 1 or 2 different ways. If I had 3 O's, as in zoology, there would be 3 times 2 times 1, or 6 different ways to arrange those O's. And I listed all of them out so you can actually see that. Right? If we had 4 O's, how many different ways would there be to arrange them? Well, there would be 4 times 3 times 2 times 1, or there would be 24 different ways to arrange those O's. Okay, so now we've seen this before too. Okay, so if we have in the moon example, if we have 24 passwords, okay, what would we need to do to find the number of different passwords? 12. Well, we divide that by 2. Right? And then that gives the number of different passwords. All right, so we've used this technique before of using division to get rid of things that we don't want to count. All right, so for the 3 O's, if we said 5,040 different passwords, 5,040 passwords, but now we want to only count the number of different passwords, we could divide by 6, right, since every one of those passwords would be in like a group of 6 that all look the same and are just different by rearranging the O's. Right, so if we divide by 6, that should give the number of different passwords, and that's going to give 840. All right. If we had 4 O's, right, so let me make up a word here. I can't think of one with 4 O's offhand, but let's say that this was like moon with 4 O's. Okay, so to count the number of different passwords, well, first of all, I have 6 different letters here, so there would be 6 factorial ways to arrange those. So that would be 720 passwords, right? But now there are 24 different ways to arrange those O's, so I would need to divide by 24 to find the number of different passwords. Okay, and then this one's actually a smaller number here. There are only 30 different passwords, so this would be a good one to check if you wanted to confirm that actually does work. All right, so I would just start with this. You'd have an M and N and 4 O's and try to write every possible password you can make out of those. All right, so for example, you could do like OM, OOON. You could try, maybe moving the M into different spots and so forth. All right, so if you are still skeptical, I would do that. I would list all of those out and make sure you do have 30 and no more than 30. Now here's another example. What about, let's say we want to make a password out of the letters in classification. Okay, so same thing, let's assume we're using all of those letters and we're counting only different passwords, and then we do care about the order of those letters. And we do want to not double count any passwords that would look the same. Okay, so for example, classification, the word itself is a password. I'm seeing that I have 2 S's in here. Right, so if I switch those 2 S's, that's actually not going to create any different password. Right, so I wouldn't want to count things like that. If I write this all out backward, that's another password. Okay, and then same thing in that one. If I switch the 2 S's, you're not going to be able to tell any difference there, so that should not be counted as a new password, just if you switch the S's around. Right. I'm also noticing that there are a couple C's here. Okay, so if I swap those 2 C's, I don't want to count that as a different password. Right. So it looks like here, since there are multiple letters, we need to take that into account. Right. So notice, first of all, there are 2 different C's. Okay, and there are 2 A's and 2 S's, right, and 3 I's, and I believe that's it for the repeat letters. All right, so first of all, let's count the number of passwords. All right, so this classification has 14 letters total. So if I did 14 factorial, that would tell me the number of passwords. And then we want to divide by the number of ways to arrange all of these repeat letters. Okay, so if I think about any one of these 14 factorial passwords. That's a large number. That's 87 billion and so on. All right, so in that whole list, every time I have a password, like let's say the second one, okay, it has a double that looks exactly the same just by switching these two C's. Right, so I need to divide by the ways to arrange two C's, which is 2 factorial, 2 times 1. Okay, so I need to divide by that. I could also make a change that wouldn't look any different by switching those A's. All right, so I would need to divide again because I want to get rid of all the repeats formed by swapping the A's. All right, same thing with the S's. I've got repeats from that. And then for the I's, we've done one with 3 before, but there are actually 3 factorial or 6 different ways that you could swap those I's around. Okay, so we want to divide by 3 factorial to deal with those repeats. All right, so to do this, you have 2 options. You could either work out the entire denominator first, right? So this is going to be 2 times 2 times 2 times 6, which is 48. So in a calculator, you could enter 14 factorial divided by 48. And then your other option is to just type this in all at once, and you would need a parentheses around the denominator. If you don't put that there, then the calculator thinks you're just doing 14 factorial divided by 2 factorial, and then it thinks that everything else is multiplied up in the numerator. Okay, so if you put a parentheses around the denominator, it will interpret this correctly. All right, so try that out, and you should get the answer. Let's see, 1,816,214,400. All right, so it's still a huge number of different passwords, but this way we've eliminated all of the ones that look the same. All right, let's do one more example. This is from your textbook. This is example 7 in section 11.1 if you wanted to refer back to this in the book. How many different passwords can be formed using letters in the word Mississippi? Okay, so we're going to use all of these letters to make the password, and different is the clue that we need to look at this special case of permutations. Okay, so step 1, you would count up the total number of letters and then figure out how many just passwords there are in general. Okay, so we would have, let's see, 11 different letters, or I'm sorry, 11 total letters here. Okay, so that would be 11 factorial passwords using all 11 of those letters. And then we need to divide so that we're only counting different passwords. Okay, so to figure that out, you would look for the repeat letters. So I've got an M. I only have one of those. Okay, I, we have 4 of them. S, we have 4 of those. And 2 P's. Oops. Okay, and then just as a tip to make sure you've accounted for everything, if you add those up, that should give you the total number of letters. Okay, so we would want to divide by ways to arrange those repeat letters. All right, so I, that's a repeat, so there would be 4 factorial ways to arrange those I's, okay, or 24 different ways. So if like Mississippi is my password, all right, I have no way of knowing whether this is like I1, I2, I3, I4, or if they're scrambled and rearranged into one of those 24 different ways. Like it could be I4, I2, I1, I3. Okay, so I've got to divide by 4 factorial. Same thing for the S's. There are 4 factorial ways to arrange those, and I don't want to count all those repeats. And then with the P, 2 factorial ways to arrange those. Okay, now there's one difference between this and what your book has in this example, and they actually say that there is one way to arrange the M, or 1 factorial, and they put that in the denominator. Okay, so notice that's not going to change the answer either way. This is just like dividing by 1. So you have a choice as long as you get the factorials for the repeat letters in the denominator, then this works out fine. And you may or may not choose to put 1 factorials in for all the letters that don't repeat. Okay, so calculating this, again, you can do the denominator by hand first or separately, or you could type this in all at once, putting a parentheses around the denominator, and this would give 34,650 different passwords that all look different from each other. Here's the formula for this case of permutations. So this is a rule for when some of the objects are alike. We've done examples with letters repeating. It could also be symbols or some other situation where we don't really care to count repeats of things. Okay, so the number of permutations of n objects, so like our Mississippi example, n would be the 11 letters in the word Mississippi, in which K1 objects are alike, K2 objects are alike, etc. Right, so here K1, this would be like, the K's represent like the repeat letters. So we would have, for the M's, we would have like K1 is 1, there's one M that's not really alike to anything else. K2 would be 4, so there would be 4 I's that look like each other. We would have a K3, right, that's the S's, and K4 would be 2, we'd have 2 P's. Okay, so then in this rule, here's the formula. So you would do n factorial divided by all of those different K's factorial. So 1 factorial, 4 factorial, 4 factorial, 2 factorial. Right? And then here's the little rule. The K's should all add up to the total as long as you're counting the ones as well. So this is like 1 plus 4 plus 4 plus 2. Oops. Adds up to the 11 letters in Mississippi. Alright, so that's it, other than just maybe let's give a name to this special case of permutations. A lot of times these are called distinct permutations, right? Or sometimes distinguishable permutations or different permutations, just something that implies that we only want to count the ones that actually look different from each other. And that's it.